Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Bernhard Steffen from the University of Dortmund in Germany. I've known Bernhard for quite a while. I think we met the first time at SAS in 1996, and it's always been a great pleasure to discuss program analysis with Bernhard. He's worked on numerous issues in compiler optimization, program analysis, model checking, and today he's going to talk about regular extrapolation of behavioral models, where he will show how to use language learning methods to understand the behavior of systems. Welcome, Bernhard.
Thank you very much. My talk today is very strongly motivated by a practical project, and some things seem to be a bit strange for a computer scientist, but I think practice showed that there's a lot of impact of these methods. And what I want to do now is to start with the application domain, the background of the project, and then explain why we developed the methods as they are. The first thing is here, the project was about a computer telephony integrated system, which of course consists of computers, telephones, and the whole stuff is integrated. And we worked in a big project with Siemens, who provide essentially the switch here. And they had big problems with the reliability of their system, because originally the main thing of the telephony system was the switch, and they had a couple of computer applications, and this was easy to control. But then with the years, the number of computer applications were dominant. When we entered the scene, there were 200 computer applications running with the switch. On the other hand side, the switch had an upgrading rate of 2 months, every 2 months a release, because of feedback of customers and so on. So they were in deep trouble to deal with what we call regression testing, so that they were sure that these upgrades still cooperate properly with the 200 applications. This was their problem. And if you are in industry, and if you are in academia, then the best thing for you to work with industry is if the water level is very high, and the water level there was in a very convenient place for us to start a project. Okay, what we did was, first of all, okay, the learning was a second phase. The first thing we did is we developed with them a test coordination platform, where they could organize the whole testing of this scenario automatically and do a lot of stuff which they had to do interactively, remotely, and all these kind of things. So we built and this was the first part, we had first a test controlling framework established with a test controller, which was able to take over the whole testing thing. This was a very successful first step of the project, because they reported an improvement in performance by a factor of 40. So they could really test quite the hell compared with before. But during the discussions, we recognized a few very surprising things. One thing was the used notion of test coverage. This was something you will laugh in a minute, because they developed 500 tests as expert of the system. The test engineers developed something like 500 tests, and test coverage was relative to that set of tests. 90% test coverage means we execute 450 tests of that set. I was first very surprised. There was all these engineers, these were telecommunication engineers, and they were speaking about, oh, we have 95% test coverage. I said, how do you do that? You have a system. One characteristic of the system was that the system was not really known to them. It was essentially to this test group a legacy system. They didn't have the code of the switch, and of course they didn't have the code of the computer applications. And then they speak about test coverage. I was completely surprised. But of course, after that explanation, things were clear. Yeah, sorry?
So what do you mean by test coverage with respect to a set of tests? Why can't I run all the tests?
They could have done 100% also, sure. I mean, they still didn't do it because test was very costly before. Each single test was really executed manually by a person who had to press buttons of a telephone, had to take off of the receiver. This was really a big effort, which was in the first part of the project all automated by means of our test generator. So we could kind of by means of, let me just switch the slides and you will see that. Already in the first part, we had here this infrastructure where we could steer with the rational robots the computer applications and where we could emulate all the computer stuff. This is another test tool, like the rational robot for computer applications for the telephony scenario. We could steer all the stuff that you could do via the telephone protocol. And together, by means of steering these two, we could steer the whole testing scenario of the computer telephony application. And okay, the first part was just getting this test execution in place. And then, of course, we discovered this nice notion of test coverage, which was a bit an historical notion. And we discussed with them the problems of that notion, and that typically if you write tests, it's like this joke where you say, why do you search for your key where it is bright? Yeah, because it's so difficult to find something in the dark. The same is with testing. If you take the test cases of the developers, then you always look for errors where there are none, because it's exactly the places which you thought about anyway. And it's very difficult to find the errors where they really are. These are the places which you forgot. And so you don't have them in your test suite. I mean, this is all known to you, of course. And so we developed the idea of we have to find a way, based on a legacy system, to get a model in order to use that model to develop test cases. This was to develop test suites, and then to describe coverage relative to that particular model. And of course, the only thing we could do with this system was to execute it and to observe it. And this was the starting point of the whole thing. So let me go here. What we called it first was moderated regular extrapolation. It's not learning, we call it like that, because what we really thought is when you deal with a system, you have finite experience, you see finite traces, and you would like to extrapolate it beyond that finite known facts to real models which interact indefinitely, because of course all these communication systems don't terminate, they should go on forever. Okay, then the other thing, it should be regular, because we want to make regular models, we can control them well, we can use all our methods, model checking, all these kind of things. And what is also new for learners is that we moderate it. Moderate means that we would like to steer the learning process by means of some knowledge of experts, application expert, or people knowing something about the architecture of the underlying system. Otherwise, learning is quite an expensive enterprise. Okay, what we saw immediately and what is true for all pragmatic learning techniques is this approach is neither correct nor complete. But it's very good. You get I mean, when you start like in a legacy system, you could think that the hypothesis model about the system is a one-state automata, just sigma star. Yeah, I mean, this is very bad. So as soon as you start carving out a bit of automata information, kind of trying to get some structure, you do better. So the good thing is, of course, always the level where you start with relative to what you have later. Yeah? If they would have a formal specification and strong models, this wouldn't be the appropriate way to go. But if they have nothing, then carving out specific patterns of behavior is already quite a lot. Okay. So what are models in our scenario? We based everything on observations on the protocol level. So at the protocol level, you find lots of information about when certain events appear, which telephone does what was the number, what was the time, what was all these kind of things. It's ISDN, so it's 64K a second. So there's lots of stuff going on. And the first thing is, of course, to make a strong abstraction. It's compared to here, you would say, going from a real program to a Boolean program. You want to have a propositional structure and to speak instead of concrete phones about symbolic phones. You want to be abstracted totally from time. We reduce time to causality. So if something was before the other, we didn't model the absolute time distance, but just the precedence and these kind of things. And this is essentially the model structure. Yeah. Should I go back?
Yeah. Where do we get the left-hand side document?
The left-hand side, I showed you this test equipment.
Right.
We had the rational robot, which is able really to feel. I mean, this screen capture stuff. You get protocol information of the application protocols from rational robot, which is part of that. This is now, by chance, a piece of the other. This is a telephone protocol, which you see by this other test tool. So you really put it on the line. It's something which is non-intrusive. You just listen to the protocol line, and you sample all the stuff, and then you abstract it, and this is the basis of your thing. So it's totally non-intrusive to the application. Doesn't change the code, nothing. You just listen to the line. Okay, so the system as such look like this. We have states, of course, and events in between, which you saw on this description on the protocol level. But we have something else which we could do with the test tools. If you have this rational robot, you can follow some events, but you can also really see what is at the screen at a certain moment, which kind of mask is currently visible. And this is our state information. So we have really orthogonally access to both, to dynamic information, which we store in the transitions, and static information, which we store here. And together we make a model. Of course, yeah, you want?
Were the protocols known to you before you started? So you could already draw these diagrams before?
This is sufficient to draw these diagrams. I mean, you can draw traces. Yeah. So what we get is you have this sensoring. You observe the stuff, and then you draw traces according to the precedence information you have. We have various sensors at various places, at the protocol, at the computer side and the telephony side, and according to the concrete time, we order them causally in this model. Yeah.
Again, you observe the system during normal use or during the existing tests?
So this is now that this equipment works in both ways. We use that stuff actually for monitoring of running systems, and we use it also in course of testing when we really kind of trigger the system in a controlled way and compare the results. It's both done here. So at this place, it doesn't matter which was the concrete scenario. And these kind of models is a starting point. So we can see here, this is a off-hook event, for example, which could be here. And here you can see a display at the phone or some mask on the computer. Okay. Conceptually, what we get is a thing which is at the same time a transition system and a crypty structure, because you have both labels at the transitions for the dynamics, and you have this independent information at the states about what you really observe at the different devices, also the visible things like display and so on. And what was also very important was the distinction between input and output. In these communication systems, you can't control input, but you have the control of the output. In fact, we will see that in our case, we have input determinism, which means when you have a given input, then you have a determined output. For each input, you know what the output is. You have no non-determinism at that level. And one thing which I don't speak about today, which we use in the course of streaming the learning process, is that we use modal transition systems. This is a way to describe not as individual transition system, but sets, because you have may and must transitions, and by means of that you can, you are more on the specification side than on the real system side. But this is, you shouldn't worry about it that now. This is just to say that this is embedded in something where we build a specification in a more general setting. Okay, this was all what I wanted to tell about this background. Now I want to say a bit about learning, very simple stuff. Then I will tell you how we make it more practical by means of optimization. And then I will present something, we have built a system which is called LearnLib, where you can experiment very nicely with learning. You can change parameters, you get statistics back, and you can see how learning behaves really in practice. This is essentially the plan for the rest. So you have an unknown system. We view an unknown system just as a generator of traces. You could, so abstract learner says, okay, we have a language. There's a language, and we want to learn the smallest deterministic automata for that particular language. This is the abstract setting. In our concrete setting, it's really the case. We did all this stuff by having as the unknown system the real computer telephony application. Sorry, I have. we had really the computer telephony application, and we used testing to investigate exactly what the system does. So now what is the idea of automata learning? You have the following situation. You have the possibility to investigate the system by observation, and here you have two things. This is the algorithm by Dana Angluin. You have two major methods. One is to ask membership queries. That is, you pose the system with a word, and you ask, is this word in the language or not? This is a membership query. This is realized in our system by means of a test. We can generate from an abstract word. This was not quite so easy because the real system works on the concrete level, not on these abstract symbolic levels. So you had to do something to kind of concretize this particular word, making it an input to the system, execute the test, re-abstract the result, and then you have the answer to that particular membership query. So this is one thing, one of the major ingredients. The other one is equivalence queries. This is a bit more tricky. Equivalence query says, I have one of those, we call hypothesis automata. This is one deterministic automaton, which might already be the description of the real system, and then you pose an equivalence query saying, is this already the automata we are looking for? Of course, if you just have a black box, there's no way that this is implementable or realizable. And we do that in this practical setting by using methods from conformance testing to investigate the vicinity of that hypothesis automata by tests in terms of the real system. For our investigation of our learned, of course, we deal very often with self-made systems, artificial systems where the equivalence query can easily be realized because you just make some bisimulation check, which is fast. But if you really deal with a practical system, you must work with approximations, and conformance testing ideas with certain coverage ideas combined give you quite a good handle to get very good results. Okay, so what is learning now about? How do we construct that automata? We get only traces, and we want to have a real deterministic automata. And in fact, what you always get is the smallest deterministic automata which is consistent with all the observations you have done. Yeah? So this is let's say, a denotational description of what comes out at any stage. And automata are described like that. Everybody of you knows this Nerode congruence. This is that you describe states by all the futures and their behavior, whether they lead to an accepting or non-accepting state, also all the language which is accepted at a certain state. Yeah, I can characterize an automata state exactly by its individual language. And this is one idea. This is reflected by using distinguishing futures. The algorithm dynamically constructs a set of futures it wants to look at in order to distinguish two states or to decide whether two states are the same or not. And the states they work on are, in fact, words leading from some start state to a particular place. So you have two descriptions of a possible state. One is a sequence which might lead you to some position in the automata. Of course, two completely different words may lead you to identical states. So in the first place, you assume that you assume everything is the same unless you find a distinguishing future. Yeah? So you select all the reaching words. You execute the system by means of some trace. You list your potential individual states, but as long as you don't have a reason in terms of distinguishing futures, you consider them all the same. So this is the distinguishing information, and this is the reachability information which kind of spans your automata. Okay, and then one other part is done in Angluin. It is tried. If you get here a kind of skeleton structure, and you complete it by means of one-step transitions. You check whether all the one-step transitions of that automata are possible and are well-defined. This is done by the notions of closeness and consistency. But I don't want to say more here on that abstract level, but I have just a small example, and you will see how it proceeds. So this is a very basic thing. We have a very small academic example here. You start first with assumption what is the assumption you have that the empty word is in the language? This is what we start here. This is not assumption. You check that whether the empty word is in the language. This would be the starting point. And now we will see stepwise how the algorithm proceeds. So the algorithm proceeds now by checking whether that is a good hypothesis automata. And the first thing it does, this is happening down here, is whether this automata is in a good way closed under one-step transition. So it looks at the possible transitions. So in this artificial example, we have just two actions, A and B, or two symbols in the alphabet, A and B. So after an A, we see it is still accepted. Yeah, we reach, by means of A, we come to a state which is still accepting. So we have not only the empty word in the language, but A as well. And now there's another symbol, B, but B is not accepted. So initially, we can only do an A. This is what we observe here. And what happens now, I click here, and you see this automata is not closed. We have only one state. And definitely, we have to distinguish two. We need an accepting and a rejecting state. So what happens is that we add this state here. So there must be a state leading to 0. And you see even the empty word is already here distinguishing future. So now the game goes on. You take a look at BA and BB. You see both are not accepting. What you now get is something which is closed and consistent. You have an automata. And in fact, it looks like this. You have two states. OK, A, it has an A loop, which is accepting. And after you do a B, everything is rejecting. This is what you get by means of those steps. Now, this is the position in which you start asking an equivalence query. We do that. And at first, you can see here how this is modeled. These are the two states. And the transitions are all explicitly modeled in the table. You can see this is just the connection between the table and how you construct from that table this automata. It's very, very simple, straightforward way. OK, when we have done that, we ask the equivalence query. This was very fast now. And it says AB is in the language. It says, yeah, here, and this is in a counterexample here because after an A, every B leads directly to the non-accepting set. So AB in the language is a counterexample. What you have to do is you put that counterexample and all its prefixes into this part of potential states. You ask again the corresponding membership queries. What we have done here already, this is already asking those queries. And then you complete again by looking whether this is closed and consistent. So the same procedure as every year. So this looks all pretty normal, but now something happens. You see that this automata we get is not consistent. What does it mean? We have two states, the initial state and the one after A, which are both accepting. But if you look at the successors, the A step from epsilon leads to accepting, but two A's in a row, that means the A step from here leads to rejecting state. So these two cannot be the same. And now something happens which I wanted also to illustrate. This means we have to enlarge the set of distinguishing features in order to be more accurate about the automatic construction. So and here you see this is, of course, also a big number of membership queries you have to ask. And you see we need this feature here in order to be consistent in the current hypothesis automata. And then you continue the whole thing. You have now closeness and consistency. You get that particular automata out of it, which is, again, in its states and transitions modeled by means of the rows and that table. And this finish now means we ask the equivalence query, and in fact, this automata already reflects the whole thing. This was just a small example. Yeah? So this is how the basic Arduino works. It uses a lot of membership queries. And in fact, this is also, of our investigations, the main measure of complexity of the algorithms. We don't deal with individual statements, but we investigate learning procedures mainly according to the number of membership queries and the number of equivalence queries it requires in order to get a certain result. OK. Now I want to briefly tell you something about optimizations. Learning never has been really used very much in practice because it's fishing in the dark. It's to some extent, and it's not very effective. So the first thing is that we thought, what can we do by means of optimization? And here in this table, there's a few characteristics. We have unfiltered events, unfiltered membership queries. each of these entries corresponds to a membership query, and the blue ones are the ones which have to remain. Then we have some which we can answer without testing, just because we know the system is prefix closed. These are the green ones. Then some are redundant. This is redundant with respect to that, because the A in the future init A is, of course, the same as A init 8 with the future epsilon. So these two things are the same, so this is redundant. So we can suppress the membership query. What?
Why is it different than prefix closed?
It is, I mean, in fact, redundance is the stronger notion. So redundance is a weaker, prefix close is a stronger notion than redundance. We distinguish that both, yeah? If you have prefix close, every word is a prefix of itself, and so we would, in this respect, this implies that. This is what you meant. This is sure. So you will see that also when we use our filters, when we use prefix closeness, we don't look at redundancy anymore. You are totally right. But we used sometimes cases where we only have redundancy and no prefix closure, and then it's different. Sure, but you are totally right. Okay, then the other thing is input determinism. This means given a set of inputs, you have only one possible response, output action. And this gives you, of course, if you saw one action, one output, you don't have for the same input to investigate all the other possibilities. There's a lot. And the other thing which is very important is we have, in particular, the telephony system, we have a lot of parallelism. We have many phones. They are all essentially similar. We want to treat them symbolically. And this means that you can use symmetry arguments to reduce the number of queries quite a bit, and also partial order arguments, that the order of events is sometimes not important. So that these two things these all we exploit. And now this is just, I want to do a colored table of the real system, but with only one phone. And the green stuff, of course, the prefix closed stuff. The blue stuff remains. The red stuff is input determinism. And you see that lots of stuff is green. And when you look at a pie chart, only 13% of the membership queries which you would have to answer without optimization have to be answered here. So you can here distinguish between the various things. OK, we did that for 2 devices, so there's only 4% left, and the 3 devices. Of course, then you see suddenly that the partial order starts building up. If you have parallel systems, then you get more. So this is, and only because of that optimization, we were able to carve out the real system, the telephony system, sensible aspect models. We didn't model the whole telephony system, but we only looked always at any point at certain aspects. For example, the correct behavior of establishing a connection. We didn't, between 2 phones. We kind of hit everything else, because otherwise these models grow very fast and learning is no longer effective. So we typically focus on individual aspects, suppress the rest, and learn on that level. Do you have a question?
So just a question about the approach again. So you were talking about initially this problem that these systems are supposed to accept infinite words, right? But at any given point in time, you've only seen finite fragments of such words. So could you, at a high level, describe to me, at least again, how the technique deals with the infinite tail?
I have to briefly go back.
Okay.
Oops, I'm not sure how fast it goes here. Then you see it immediately. This animations are terrible. Sorry. But you see it very easily at the very beginning. Or you can take just here. We observed only these are all finite sequences. None is longer than 3.
Yes.
But because of the assumption that the state is the same, if there is no distinguishing feature, you introduce a loop. You introduce a loop. And in fact, I wanted to go to the first place. In the first place, it was even, you have just one state, it was just sigma star. And so you are very, very brutal in establishing loops. You don't establish them only if you have a reason to extract. Now I have to go back, but this gives you a chance. So what I want to tell you now is about the system we built. So this is just stuff we did, and which led us to which convinced us that we should build a system which we call LearnLib, which allows us to play with various options. One other option, which I just mentioned here at the side, is you can have different automata. We typically dealt with DFAs, deterministic finite automata. If you go to testing people, they very often deal with mealy machines. And so, for example, in this telephony scenario, it was a case that the mealy setting with this input-output distinction was much closer to the real system. And for example, so we adopted, for example, learning also for DFAs and for mealy. We had a separate system which did mealy learning, which is even another order of magnitude faster than for this telephony system. It helps quite a bit. This is not yet published, but we have done some experience about it that mealy learning sometimes really accelerates the stuff quite a bit. You have to make some real adaptations. You don't have Boolean tables anymore. Of course, you deal with words and you need some other stuff, but it's not really difficult, but it's really a big step forward in performance. So there were lots of things. So we built a system. Here is the library view of the system. We have algorithms in the LearnLab. Then these are the classical learning algorithms. Invariance, here the DFA, the mealy part, mainly based on gluing. There's other learning algorithms. There are other methods, the observation pack algorithm, discrimination tree algorithms. They are not yet implemented. We have mainly versions at the moment in the library which are ungluing based. Then we have a number of filters. You saw some of them in the previous slide. And we have a whole set of different approximations of the equivalence query. I told you this is the major weakness of learning, that this is not implementable. So we used various ideas of test coverage and conformance testing here to get various different filters, equivalence queries realized. And on top of that, we use two things. One is the real thing, which we did with the telephone scenario, that we really want, by means of testing, to learn and carve out models from running practical systems. There you need these approximate equivalence queries. We did that with this telephone scenario. We did it for web applications. Some of you might know this online conference service which we built and which, for example, ETABS uses. We checked that also. We learned aspects of that. And we have some other things. At the moment, we are learning hardware. We have a chip, and we learn certain behaviors of the hardware. OK. And then we have a simulator scenario, which is very good to evaluate various techniques. You don't want to use all this testing. I mean, executing a test on a real system really costs time. You really have, so telephone must ring, even if you only look at it at the protocol level. It's really things going on here. And one test, sometimes we had tests running almost a minute. And these were the very long counterexample things. And this is, of course, not, you can't do statistical analysis if one of those entries in your table costs that much time. So we do a lot of simulation in systems which are we just randomly generate automata and use them for learning. And this is this scenario. Oh, yeah, OK, we have the random models. Of course, we used also a few automata which we just took from some libraries, like some protocols. Perhaps you know the CADB toolkit from Hubert-Garavelle. So we used also some models there and tried to carve out from those the behavioral patterns. But of course, in this setting, equivalence queries can be answered really properly. OK, the other thing is we have two modes. We have an automatic mode, which is, of course, particularly important if you want to execute tons of statistical tests. This is mainly that you organize all your membership queries until you get consistency. This is a classical ungluing. And then you introduce some equivalence query, which goes through the filters which you want to see here. And we have, OK, this is easy. This is easy to build into a frame program which does all the statistics for a big number of tests. And we have an interactive mode where you can individually at each time say which kind of optimizations might be interesting. So if you want to look at a bit more into the individual behavior of optimizations and queries at certain points. We support both. Mainly we used up to now the automatic mode because we wanted to get big statistical results. OK, but this interactive mode, you can easily modify and write essentially testing processes which tell you when you want to apply what, and then you can put this in place. And this modification is very easy, and you can flexibly get to new learning algorithms, if you like, or versions of learning algorithms. Okay, you do that. The configuration is just by means of such a graphics. You describe essentially as an automata at which point you want to execute which filter and how you want to combine these results. Here it's this is actually some kind of parallel composition. You use these filters before you do the result. Okay, and if you do that, then you can execute tests. Here we have just an overview, a statistical overview, which resulted from lots of test cases with different numbers of states. Each entry here corresponds to a certain number of states. For example, we have here 180 states, here 150 state automata to be learned. And for each of those vertical line, we used 100 randomly generated tests of that particular size. And then we investigated how many equivalence queries were necessary in order to get to the real result at the end. And here these big lines are just the average. And here you see there was, in order to learn a 180 state thing, there were also cases where you need 17 equivalence queries, but no more, and so on. You can see each of these entries tell you how many equivalence queries you needed. But this is not really quantitative, because you don't know how much or how many of those queries were at these points. So we have another chart which is also automatically generated, where you can really see precisely how many queries were used. For example, in the case of automata with 50 accepting states, the number of equivalence queries we needed, and the number of cases where we needed 10 equivalence queries were 330. Yeah? So you can here really get a very precise statistical analysis how the learning behaved. And this is very interesting if you introduce a new optimization to see how much impact that has. Very funny, this is unfortunately not on those slides because we still want to publish this. If you go to mealy, these figures get completely different. This is pretty funny. You get the number of equivalence queries really kind of gets really drastically reduced. Okay, here you have the distribution. You can also look for all these scenarios whether really there has been, to what percentage an equivalence query was asked to a precise size of the state space. So here, for example, it says in 1% of the cases we had to ask an equivalence query with 28 states in the hypothesis automata. One thing is sure, if you have 128 states, you always need to ask an equivalence query with 128 states, because this is the one which finally gives the result we are there. So this is why it's here 100%. And you can here exactly get results in the Learn Lab to understand better how this algorithm behaves. And in fact, the algorithm, if you deal with that, the algorithm is not so simple that you really, without any of those means, get a very good intuition. It is a fact that playing with it gave us quite a number of insights which we didn't expect. For example, this smashing down of equivalence queries just by going to mealy was far beyond what we expected. Okay, then here is something else. Here is, you can in particular see the impact of the prefix closure, because this is a logarithmic number. Yeah, this piece is much more than all this purple stuff below, because this goes from 80,000 to 1.2 million. Yeah, so it's a factor 20 times the stuff below. So this says, in this case, alone the prefix closure reduces the effort of learning by 95%, or reduce it to 5%. This is another overview. I don't want to go in too much detail to all these things. So here, another view on the number of equivalence queries. Here is a third chart which we pre-implemented, where you can really see here's abbreviations of the filters we used. Everything which contains a P uses prefix closure. This is prefix closure plus independent. This is prefix closure plus symmetry, and this is prefix closure plus independence and symmetry. And you see, the main thing is prefix closure at that point, because it makes a big difference. Here's the same stuff without prefix closure. Yeah? You see, prefix closure is very dominant, but there are, of course, also systems which are not prefix closed. So in this case, the other optimizations are very important. However, if you really think in terms of investigating systems by observation, you will always be dealing with prefix closed system, because I can't observe ABC without observing AB. So if you look at systems by traces you might observe, you are always in this very good case. And this is the good news and the hope that you get practical good results. And the symmetry and independence filter is here comparatively weak. This is because we used still in these examples very few parallel components. As soon as you have more parallel components, yet the most we did up to now were 3 phones. If you go to 10 phones, then the impact of those is, of course, enormous. Yeah?
Can you remind me again what the numbers on the y-axis denote?
This number here.
Yeah.
This is the number of membership queries.
Okay, good.
So this means that it is 3.2 million membership queries.
Got it.
And you had to do here 300,000 membership queries.
Got it.
Okay. So this was just, I mean, what I wanted to show you. We have this system. It will be, hopefully, not perhaps this year, but we want to present it perhaps at ETAPS. We want to have it online so that you can do all these experiments with your browser. So we want to have a thin client, and you can, via your browser, do all this stuff and get HTML charts back here.
How sensitive like each equivalence query or each membership query?
What?
In terms of time.
Yeah, I mean, there's 2 completely different cases. If you are in the realistic case where we approximate it by conformance testing, it's enormously expensive. You have thousands of membership queries sometimes. Yeah. If you take it in terms of the simulation mode, we have page target, and then it is very fast because you just it is a log en and then a log ne. So it's complexity-wise not right, and the observation is also very fast because the number of states we have is a few thousand. Page target on 1,000 states is very, very, very fast. So in the simulation mode, it is not really a hurdle. In the practical mode, first of all, it's only approximative, and second, it's also very expensive. Yeah. So this is, and this is something where one has to see, and this is also the place where we very much want to use more of the moderation. We use temporal formulae in order to steer where to look. So we say we know that this system should be able to do certain things, and we know that we should extend the current hypothesis automata in a certain way, and then we search in a tailored way counterexamples. In fact, before you want to really verify that you are there, the main thing of the equivalence query is to find counterexamples. Like in model check, and so you can use any method. You could also use. You just want to be fast at a counterexample in order to improve your current hypothesis. And only really, you must only be comprehensive in the place when you think you are there, or when you have the chance to be there. And of course, with the equivalence query, we simply stop when we find an error. So in this respect, in practice, not quite as bad as one would expect, because in the very first place, you find extremely fast counterexamples. Okay. Now, we developed all the stuff really in a practical project, and this practical project belongs to our whole, let's say, system landscape. We work actually, or we have a software development environment, which is, if you like, a service-oriented, let's say, a framework for service-oriented software development, where you build here service-oriented models out of given components, and you control the whole process by means of constraints, typically temporal constraints. And the construction of those models, which might well be hierarchical, is all the time be controlled by means of those constraints. You can construct from here views, because these models get large. We have here sometimes models of a few thousand states. Each of those states being, in fact, whole software modules. So it's not the case that there's a small programs, because one of those components might have 10,000 lines of code. This is something we did for the definition of value-added services with Siemens already a few years ago, that we built models on top of real basic functionalities for value-added services in telecommunication, like 0800 numbers and so on. They combine things like time-dependent routing with blacklisting on these kind of features, which you know perhaps from telecommunication. And when we have those models in our system, we can automatically deploy the system, of course, provided that we have installed everything properly. And on that level here, this is what we discussed today. Here we can monitor and test the system by means of learning. So we can use these models for monitoring, but we also can monitor by observation. We compare, at this level, we have machinery in order to trace exactly what is going on, and we might compare that with a previously learned automata or with a model we have constructed ourselves. Okay. And the whole thing what is behind our system is that we try to design software from the point of view of the user process. This is what we call coordination of the application functionality. So we have down here is all the real software stuff, the libraries. And up here, we construct in our system complex applications by composing application-level functionalities to behavioral automata. And this is the case, or this is the reason why we can use those models also in order to monitor or in order to steer testing. So we can use those, exactly those models for test generation. Okay. So this was just some background from why we came to that position and why we had all the infrastructure to really and realistically test these systems. Okay, now a few words of conclusion. The main thing we started the project for was that we had problems with the notion of test coverage and test generation, because this was solely done just by test engineers according to their stomach or whatever part of the body they used. We wanted to make that more systematic. We convinced them that models are great. And one outcome of the project was that they completely revised their test suite. We saw that the test suite they built, according to the models we constructed, was extremely partial. They did quite a bit in a certain error and even redundant stuff, and they completely missed huge parts of the system. And so they revised their test suite dramatically. Another thing is we can use that also for test evaluation. The main thing, or the main benefit for Siemens was the support for regression testing. I told you that every 2 months you have a minor modification of the system, and you want now to check whether all the old stuff is still working. So what you did, or what we did, was we ran the test on the real new system and compared it with the learned model of the old system. And this was very fast, and in particular, it eliminated big numbers of false positives. Why? What they did before in regression testing was they let the old and the new system run in parallel and compared bitwise what's going on. And if you have lots of parallel components, you have kind of impact of races, independent, also unnecessary or unimportant changes of actions, and these were all errors for them which they had to investigate. They had huge numbers of these false positives. In our learned models, they are not present because we build models which kind of filter out beforehand all these independence. If you have independent actions, the model would tell you that. We did that in a very primitive way for Siemens at that point, just by adding both traces. We say this doesn't matter. We have, if there's AB, we also have BA, and we kind of completed it up to this partial order, and this made the test evaluation extremely more efficient. Okay, then we use the stuff for monitoring. And the other thing what you can do is you can, now on this hypothesis automata, you can throw all your verification methodology. You can make model checking, you can make equivalence checking, and can validate assumptions about the system on that level. Of course, you don't verify the system, but you verify it according to some independent knowledge of the system which you got by observation. This is already quite something. I mean, and this is all you can get here. And this verification, of course, gives you sometimes results that a certain property is not true. Yeah? And if you find that, you get in the model a counterexample, and then you can take that actually as an input for the next learning step. You say, oh, I have in my hypothesis model, this doesn't satisfy a certain vital property. Does it mean that the system is the same or not? So you pose this to the testing or a learning machinery, and then you can, in a very steered fashion, incrementally enlarge the model, and it gets more stable in the course of running the learning methodology. Okay, so this is a very good method to make change management on a level which essentially doesn't cost a lot of manpower. I mean, when we discussed with the Siemens people, and we knew, or we learned that they stopped documenting any kind of changes anymore. I mean, the system was 18 years old at that point. And I mean, for an academic person, was terrible to see the state of documentation. Yeah? The documentation was for a system which was built 10 years ago. So it was, and when you know, but when you learn there's this 2 months cycle of upgrading, you also know how it comes. If you now have a possibility, at least at the behavioral level, to almost for free trace all the stuff that's going on. This is, I think, a very promising approach to deal with these kind of changes. Okay, finally, gets more technically, we see still that learning is very expensive, but we try to use a lot of properties in order to get more practical, and we are convinced that there's lots of stuff possible, in particular if you don't want to learn the full functionality, but a very tailored fragment. Yeah, carve out some regular pattern out of the whole system. And, okay, I told that already. You can now, to some extent, via that learning method, also validate or verify certain properties of real systems where you don't have any specification. Okay, this was all.
I was wondering if you could say just a few words about, you mentioned this already, but at least I didn't really understand what you said, about looking at real systems where you cannot perform the equivalence query. So you're talking about the fact you had approximations to the equivalence query. Say a few words about where they came from, how you did this.
So when we started, we did something very simple. We just said we take the system and look just one step beyond. We just go to these places, and the point is you just look at the direct environment of the current system, whether this is still okay. So we just said, okay, learning does the consistency of the automata, whether the state is still there, and we just make one step more. This is, to some extent, it's not very much. We saw that in very many cases we got very good results. So but of course this is not very much. Yeah, this is but the other thing you have to keep in mind is the only thing you can do is you can test futures, and the longer the future you make, okay, the more expensive it gets. In fact, it is exponential in the size of the future. If you want to check the facility of 3 steps, then it is of course exponential in 3. This is something.
Is that like a very local sort of fixed point check?
It's
like saying if I make one more test,
yeah,
I have no reason to change my hypothesis, and then I'm
to some extent you check such a kind of invariance property, but and you check. I mean, you have an invariance after you did the membership queries in Angluin. It is close and consistent. So in some extent it is invariant to the one-step transitions. But now you enlarge your criterion, and you do that only. You try to do it very, not so frequently.
So did you use any other techniques?
Yeah, we use. I mean, there's you have the way to construct. This is really systematic ways to construct for a given system a conformance suite.
Right.
This is more than what we did. Yeah. So this is you have a model, and you want to know. Of course, this is also assumption based. Under which assumptions I can test now whether the system, the model is indeed conformed or conforms to that black box.
Right.
And but there you have the same thing. For the conformance suite, you also have to specify something about the number of states you might expect in your real system. And if you deal with those numbers, you get very easily this exponential blow up. So what we want to investigate in more depth, we've played a bit with it, is making a blind search. You have 128 states, and at each state you want to make this exponential investigation is ridiculous. So what you want to do is now, we say, we want to have abstract knowledge in form of constraints, in form of temporal formulae, which tell you under which under which steps you might expect no interesting behavior. And then you pose those constraints and use those constraints in the selection of the relevant futures where you might find discrepancies. This is going the way of moderated learning or taught learning. You have a teacher. You want to the constraints give you the teacher, and this I think is very, very important, because we can deal with the fact that learning. I mean, if you take equivalence query as a constant thing, yeah, one query, then the whole stuff is just polynomial. Not polynomial, it's just cubic. This is not bad, but the individual equivalence query is a problem. Right. And so we go with this constraint way. This is also the case when you look at the learning literature. Learning is expensive. They have this notion of combination locks. If you certainly enable something after a very specific sequence, then you cannot observe that unless you really followed the whole sequence. If the sequence is long, of course, you have an exponential factor in that, the length of that particular key. And so this is the killer in learning, to find that. But if the teacher knows where the keys are, then it's not so bad after all. Okay, this is.
Any other questions?
So you applied the models you learned to help evaluate the test suites that Siemens was using and better coverage and was there any point where the models that were learned were erroneous or mistaken or caused extra effort to be taken on the test?
The point is, in fact, it doesn't really matter. You learn some structure. The structure gives you hints how to construct your test cases or your test graphs. We actually don't deal with test cases, but we really make test programs which themselves comprise a number of test cases. So, in fact, you could guess them. I mean, formerly they did it just by means of stomach. Yeah. Now they have some hint how to do that. If you get it, you can't generate something which is really a wrong test, because every system should even accept an ape test, as we say. Yeah? So the system must be able to deal with everything. It may be the case that you make a test which fails, and failing was okay. But I mean, this doesn't matter. So having models which are neither correct nor complete don't matter very much. They only help you to identify, let's say, all the spots which might be in the system. As I told you before, the test developers, all these people, they had a very particular view of the thing, and they put all the testing effort in the stuff they anyway, and found other stuff only after they've had big trouble finding some strange behavior. With these models, they were suddenly aware of things which they didn't thought of, and so this is already quite a big thing. So in this scenario of using it to generate tests, the fact that the model might be wrong is not a big problem. It's just a hint. It's just a guidance. Yeah.
In your data, so let's consider that you had a series of events that would happen. So maybe A, B, and C happen typically, and you pick that up. But sometimes you get A, B, D, and then C. And D doesn't really change anything, but it just it's thrown in there sometimes as an interstitial. Would what you've described actually collapse those into one, or would you now have two patterns that describe those two phenomena?
You have now a system A, B, and then you have a branch for C and D. Yeah. And this wouldn't, in our cases, in the practical cases, this wouldn't be possible if D is an output, because it should be input deterministic. But in terms of input, this would just add this additional possibility.
Thanks, Steve.